Good. Okay.
So we can slowly start. The students are joining. Some of them are here in the halls and library also.
Okay.
So it's truly is a pleasure to welcome Professor Girvin to this QIQT forum. And as you realize, Professor Girvin has fundamental contribution to both theory and this super quantum computer, development of quantum computers. If some of you are familiar, you will see circuit QED has played a very fundamental role in the current development of quantum technology. For example, with this IBM quantum computers and other things, they are fundamentally based on this circuit QED. So this really made macroscopic quantum systems possible. And many of us here, we have followed his papers on circuit QED and other things. Personally, I have been acquainted with his work since the early 80s. Just now I was mentioning to him about his work on this nonlinear algebra, which came out in fractional quantum Hall effect in many body correlated systems. So, if you see in his long career of very significant contributions to science, both in correlated systems, circuit QED, now, for example, physical systems, including molecules and the development of quantum physics of microwave electrical circuits to whatnot. I mean, it's truly a remarkable career. And today we have been really fortunate to have him here. And I have almost followed all his works because I have very strong interest in his things. Many of our students have gone to Yale. For example, our student Sriramana Muralidharan, quite a few. And Shruti Puri, his collaborator in theory, he also happens to be doctor of Professor Puri from here, who was, helped in forming quantum foundation and quantum optics groups in India. So without much ado, I request Professor Girvin to start his talk. Thank you, sir.
Thank you so much. It's for the introduction and for the kind invitation to join you today, virtually at least. And so I'm going to try to give you a pedagogical introduction to circuit QED, circuit quantum electrodynamics. It's basically using ideas from quantum optics, but applied to not lasers and natural atoms, but rather microwave photons and synthetic atoms, artificial superconducting qubits. And this is a collaborative work with many, many people. A few are listed here, including my colleague Shruti Puri, who's been a wonderful addition to our faculty. So, and the experiments, I work very closely with the experimental groups led by Michel Deveray and Rob Sholkoff. And I'll tell you about an experiment from the Sholkoff group near the end. So I have various lecture notes on this topic. If you just go to my website, you'll be able to find copies of the lecture notes and also some videos on lectures on error correction and other topics if you're interested. So here's the outline of the talk. I'm going to try to give you an introduction to first quantizing electromagnetic oscillators, then Josephson junctions and what are the transmon qubit, then learn how to do cavity QED with these by coupling the qubits to microwave resonators or cavities, and then some applications in quantum simulation. Let's see. So if there are questions, something has appeared in the chat, but I can't see it for some reason, so I'll just keep going. But if there are questions, you can interrupt. So we'll start by thinking like quantum electrical engineers and think about quantizing an electromagnetic oscillator. It could be a lumped element circuit with an inductor and a capacitor, or it could be an electromagnetic mode of a trapped in a box in a superconducting resonator that just acts like a box with perfectly reflecting mirrors for microwaves. And the coordinate of the oscillator here would be the electric field, perhaps at the center of the cavity. We'll see here in the lumped element circuit that we can define a coordinate as the generalized flux through the inductor in the form of the time integral of the voltage. So the velocity of this coordinate is the voltage, and that's just Faraday induction. The time rate of change of flux in the inductor gives the voltage up to some minus sign that we won't worry about. And the electrostatic energy, which is 1/2 of the capacitance times the voltage squared, that looks a lot like the kinetic energy of a mass moving at some velocity. And the magnetic energy, which is the inductance times the current squared, looks a lot like the Hooke's law energy stored in a spring. And so the Lagrangian is 1/2 the capacitance, the time rate of change of the flux squared, minus this inductive term proportional to the coordinate squared. So we can, to quantize this, we first have to find the momentum conjugate to the flux. And I'm going to name it Q for a reason you'll see shortly. And the momentum is the derivative of the Lagrangian with respect to the velocity. And it's just the charge, the capacitance times the voltage. So it's nothing, it's literally the charge across the capacitor Q. So that's why we named it Q. And this charge is canonically conjugate to the magnetic flux in the coil, forming the Hamiltonian in the usual way from the Lagrangian. I get charge squared over twice the capacitance. That's the kinetic energy of this oscillator. It actually represents the electrostatic potential energy stored in the electric field. And then the potential energy in this Hamiltonian is actually the kinetic energy associated with the electrons flowing through the coil and producing magnetic energy. So it looks like an oscillator with a mass equal to the capacitance and a spring constant equal to 1/, the inductance. And that gives a resonance frequency, which is the usual 1/, the square root of LC that you're familiar with from classical circuits. And Hamilton's equations of motion are just represent Faraday induction and conservation of charge. As the current flows in this direction, the charge decreases on the capacitor. So if I look at the classical equations of motion for the current and the voltage, I see that just from dimensional analysis, the ratio of the current scale to the voltage scale has units of electrical impedance. But this has nothing to do with dissipation, because the current and voltage are 90 degrees out of phase. There are no actual resistors in the circuit. This quantity, which is equal to the square root of the inductance divided by the capacitance, is called the characteristic impedance of this resonator. And in a typical, since we're being quantum electrical engineers here, we'd like to know what is that value in SI units, and it's around 100 ohms, 50 to 500 ohms. And this is intimately related to the fact that the impedance of free space, which is the square root of mu naught over epsilon naught, the permittivity and permeability of free space, being 377 ohms. There's a quantum of impedance, the von Klitzing constant, h over e squared, from my previous life in the quantum Hall effect, of about 25,000 ohms. And it turns out that the quantum impedance multiplied by twice the fine structure constant gives the impedance of free space. So there's an intimate relationship between the fine structure constant alpha, 1 over 137.059, and the von Klitzing impedance, and the impedance of free space, which is close to the impedance of any reasonable circuit that you can build. So we can now quantize this oscillator by promoting the momentum and position to operators that do not commute. And we can relate these coordinates to the photon, the oscillator raising and lowering operators, A plus A dagger, times some quantity, which turns out to be the scale of the 0-point fluctuations of the flux and the 0-point fluctuations of the charge. And the product of these two is h bar over 2. So you can calculate these uncertainties, and they are related to this characteristic impedance that I told you about. The charge uncertainty in the ground state is inversely proportional to this, and the flux uncertainty is proportional to this. So if you calculate the uncertainty, the quantum uncertainty in the charge on the capacitor in units of electrons or Cooper pairs, you'll find out that it's related to the square root of the inverse of the fine structure constant. It's a few, like 3 or 4 for typical impedance of a circuit. So there's some 0-point uncertainty in the flux and charge coordinate and momentum of the oscillator, and it's a few electrons, for typical oscillators. Okay, we'll come back to that. So quantum harmonic oscillators are very useful. They store photons. They have energy linear in the number of photons, but it's impossible, because all the transition frequencies are the same. It's impossible to achieve full quantum control over the states of the oscillator using classical signals. If you send a classical microwave drive, you cause transitions from 0 to 1 and 1 to 2 and 2 to 3. You cannot just create, let's say, a photon Fox state where there's exactly one photon. You can only produce coherent states, okay? So in order to achieve universal control and make arbitrary quantum states in our oscillator, we need an auxiliary qubit or anharmonic oscillator, and that has different transition frequencies, so that if you drive this first transition from 0 to 1 excitation, the same frequency will not be off resonance for the next transition. And you can approximately say that there are only 2 levels in this system. That is, it acts like a qubit. So how do we do that? Well, we need to replace our LC oscillator by something that has a nonlinear inductance, an inductance whose value changes with the current. And it turns out that the Josephson junction plays that role. You have two pieces of superconductor, in this case aluminum, separated by a thin oxide tunnel barrier that allows Cooper pairs of electrons to coherently tunnel from one electrode to the other. And you create an antenna, a dipole antenna, about 1 millimeter in size, and you connect the two halves with this tiny Josephson tunnel junction, which is only a couple hundred nanometers on a side. It's about 1,000 atoms in width. And the Josephson junction replaces the phi squared over 2L inductive energy with a cosine of phi, a cosine of the coordinate, and that's a softer potential, which causes to be give you an anharmonic oscillator, which we arrange to be in the microwave regime, gigahertz frequencies. And if we remember that 21 gigahertz corresponds to an energy, when you multiply by Planck's constant, that corresponds to a temperature of about 1 Kelvin. So we need to cool this system very close to absolute zero, well below 1 Kelvin, in order to be in the ground state. So circuit QED is studying the analog of cavity QED. We trap microwave photons inside superconducting resonators, and we couple them to synthetic atoms, Josephson Junction qubits. And we can obtain ultra-strong photon atom coupling and do nonlinear quantum optics at the level of single photons. So here you see a kind of semi-classical picture of a hydrogen atom, which we want to compare to the collective superconducting oscillations of electrons sloshing back and forth, Cooper pairs sloshing back and forth in our transmon circuit. So here the transition frequency is a petahertz, 10 to the 15 hertz. The lifetime of the 2p excited state of hydrogen is about 1.6 nanoseconds. That core, if you approximated this as a harmonic oscillator, it would have a Q of about 4 million. And the transition dipole moment to go from the ground state to the excited state is about 1 dBi, 1 electron times 1 Bohr radius. Let's compare that to this electromagnetic oscillator we just discussed. It has a frequency of about 7 gigahertz, a typical lifetime of the excited state of about 300 microseconds if you have it trapped in a cavity. And that corresponds to a similar Q, but the transition dipole moment is about 30 million dBi, because I mentioned the charge uncertainty on the capacitor plates is several electrons, and the distance scale is 1 millimeter. So this gigantic atom with its attached antenna couples very, very, very strongly to the centimeter scale microwaves, giving us a very interesting new regime for quantum optics. So as I mentioned, the Hamiltonian looks like an oscillator. Here's the charging energy squared, but instead of phi squared over twice the inductance, the Josephson junction Hamiltonian, the Josephson effect, gives you an energy cosine of phi, the flux. And that gives you this anharmonic oscillator. Typically, we take the Josephson energy to be about 100 times bigger than the energy of a single electron charging this capacitor, called the charging energy EC. And in that regime, you can sometimes expand the cosine, and at the second order term looks like an inductor, phi squared, and then the fourth order term looks like an nonlinear inductor. It gives you what's called four-wave mixing in quantum optics and leads to all sorts of interesting and useful effects. So here's a micrograph of this so-called transmon qubit with a small Josephson junction here. It's evaporated on a sapphire substrate, which is placed inside a superconducting aluminum resonator on a sort of centimeter scale. And the vacuum Rabi coupling, the dipole matrix element that lets a photon in the cavity be absorbed by the atom or re-emitted by the atom, is about 100 megahertz because of this extremely strong coupling of this antenna to the microwaves, this millimeter-sized atom. So the Hamiltonian, if we pick out one mode of the oscillator, it's a resonator. It's a harmonic oscillator with some frequency. If we approximate the anharmonic transmon oscillator as a two-level qubit, we get a Pauli matrix describing its state. And then we have the dipole coupling, in which you can flip the qubit and emit or absorb a photon. That's the Rabi Hamiltonian. And then we have various damping terms, which we don't like, but we have to live with. You can make what's called a rotating wave approximation on this Rabi term and obtain the so-called Jaynes-Cummings Hamiltonian, famous in quantum optics. And we'll work in a regime where the qubit frequency and the resonator frequency are very different. Like one is 6 gigahertz, the other is 5 gigahertz. And their detuning is much larger than this 100 megahertz coupling. And in that limit, you can make a Schrieffer-Wolff transformation, a unitary transformation to sort of diagonalize this term, remove the first order coupling, giving a second order coupling term called the dispersive Hamiltonian. In this approximation, the coupling is now diagonal. It's sigma z times the photon number. And we'll spend some time now thinking about this Hamiltonian. So this is an unusually strong coupling. It's the strength of this dispersive coupling is thousands of times larger than the decay rates of both the cavity and the atom. And one interpretation of this term is that the coefficient of A dagger A, which is the resonator frequency, now has a term that is bigger or smaller depending on the state of the qubit. So the cavity frequency is here if the qubit is in the excited state, and here if it's in the ground state. And they're separated by thousands of line widths. So it's very, very strong coupling, even though the cavity and the qubit are strongly detuned from each other. And as a result of this, we can read out the state of the qubit by measuring the cavity frequency. That's how we do quantum non-demolition readout of, we measure sigma z by measuring the cavity frequency. There's a different interpretation of this very same Hamiltonian, which is, it's not that the coefficient of A dagger A depends on sigma z, it's that the coefficient of sigma z, which is the qubit frequency, depends on A dagger A. That is, for each photon that you add to the resonator, the frequency, the transition frequency of the qubit changes by this dispersive shift. And so by measuring the energy that it takes for a photon to be absorbed by the qubit. By measuring the qubit spectrum, we can count how many photons are in the cavity. So we can use this dispersive coupling to measure the qubit using the cavity, or measure the cavity using the qubit. And so here you see a spectrum of the qubit in the microwave regime, and you see the transition frequency is here when there are 0 photons in the cavity. Here, 1 photon, 2 photons, 3 photons, 4, 5, 6, 7, 8 photons, separated by this dispersive coupling. I claimed that this was thousands of line widths. It doesn't look like it this here, and that's because the graduate students were impatient and took the spectrum very quickly, and these lines are what are called power broadened. So you can see from this that microwaves are not waves, they're particles. You can count the individual microwaves in the cavity using this method. And here's a different spectrum with less power broadening. And this ability to count individual microwave photons is finding novel applications in searches for dark matter. There's a certain type of dark matter hypothesized called the axion, which converts into a microwave photon in the presence of a magnetic field. And people are now using this idea to search for these dark matter particles. That's an interesting application of quantum sensing technology from circuit QED. Okay, so now that we have this strong dispersive coupling where the frequency of the cavity depends on the state of the qubit and the frequency of the qubit depends on the state of the cavity, this gives us universal control. We can create non-classical states of the cavity. We can synthesize arbitrary Hamiltonian dynamics to do quantum simulations. And we can do very efficient state tomography. And I'll show you an application in which we can make quantum non-demolition measurements of the photon number and do a very efficient, exponentially fast binary search to determine, resolve the photon number. So this simulator I'm going to talk about is to simulate the vibrational spectra of small molecules, a problem of interest in quantum chemistry. So here's the water molecule, and there are 2 hydrogens, and they are connected by chemical bonds to the oxygen. And there's a symmetric stretch vibration in which the 2 hydrogens oscillate in and out, changing their distance in phase with each other from the oxygen. And there's an antisymmetric bending mode where the bond angle oscillates this way, but the length stays approximately fixed. And there's a mirror symmetry in the molecule that protects these 2 modes and keeps them from mixing. That will become important momentarily. So the experiment we want to simulate is spectroscopy, in which we send in a high energy photon and it ejects a bonding electron from one of the bonds, let's say the one on the left here. This breaks this mirror symmetry. It changes the spring constant of this hydrogen mass oscillating against the oxygen. And it also changes the equilibrium position of the hydrogen because it's weakened the bond. And by breaking this mirror symmetry, it now mixes these 2 modes. So, and leaves behind, as you eject the electron, it leaves behind vibrations in the molecule, and the energy of those vibrations are taken away from the kinetic energy of the electron. So by measuring the kinetic energy of the electron, we can find out the vibrational energies left behind in the molecule. So this is a common experiment in physical chemistry, and we want to do a quantum simulation of it using a little simulator that has 2 microwave resonators, a beam splitter, and 2 ancilla transmon qubits to give us universal control. So each of these mechanical oscillations you can think of as a phonon or a bosonic mode of the molecule. The vibrations are mechanical oscillators. We're going to approximate them as harmonic oscillators. And each quantum in here, each phonon, we will represent by a photon, a microwave photon in one of these 2 modes. So this, if there are 3 photons in here, it represents 3 phonons in the symmetric stretch vibration mode. And if there are 2 photons here in this cavity, it represents 2 mechanical quanta in this antisymmetric bending mode. Okay. So we're going to use one kind of boson, microwave photons, to simulate the dynamics of another kind of boson, the mechanical quanta of these vibrating molecules. And it's a relatively simple apparatus, as you see here. Okay, so if I go back here and I remember that the nuclei are moving on a certain potential energy surface formed by the bonds, the electronic bonds here, and there's a coordinate indicating how much the symmetric stretch is displaced, and another coordinate indicate how much the bending mode is displaced. You get these 2 coordinates of these mechanical oscillators, and the nuclei are moving on this potential energy surface whose symmetry axes are aligned with these 2 coordinates. So there's a bending mode which has a softer spring constant, and a stretch mode which has a stronger spring constant. But after the symmetry is broken by ejecting an electron here, the 2 modes are no longer symmetry protected, and they get rotated, they get mixed together, and the new potential energy surface has a completely different shape and is no longer, it's rotated, its symmetry axis is no longer aligned with the original coordinates. So to obtain you start out in some eigenstate of this Hamiltonian, and you end up in a superposition. Suddenly the Hamiltonian changes. You're in a superposition of eigenstates of this different Hamiltonian. And so we have to allow for different spring constants and for a rotation of the modes between to a new symmetry axis, and a displacement of the potential energy surface. So there's squeezing, rotation, and displacement. And so our simulator wants to perform the unitary transformation that takes you from an initial state that you have prepared, let's say a Fock state with 2 quanta in one mode and 1 quanta in the other mode. You have to execute this unitary transformation that projects you onto the eigenstates of the new Hamiltonian after the photon is absorbed. You check, we have certain error flags that we can check after this has occurred and reject 5 or 10% of the data if an error occurs. And then we have to measure the number of photons in each resonator to represent the number of phonons in each mode. And this unitary transformation is pretty complicated, as a squeezing of the first mode, squeezing of the second mode, a beam splitter to rotate between the 2 modes, breaking the symmetry, 2 more squeezing operations, and then a displacement of each mode. But these are all quantum optics operations that we can do very efficiently in this simulator. And here are the results for water, starting in the 0, 0, the vibrational ground state. The solid black lines are the ideal spectrum calculated on a classical computer rather easily. It's a small problem, knowing the Hamiltonian. And the purple dots are the results of the quantum simulation. And you see they agree extremely well with this spectrum, which contains 256 lines. The L1 norm distance between the ideal spectrum and the simulated spectrum, the deviation is about 5%. The red curves are a exponentially more efficient sampling scheme in which we do a binary search for the photon number and achieve the data 32 times faster, but it comes at a price of a little bit more error, about 15%. So I want to thank the experimental group who give me things to talk about. It's the Rob Sholkoff group. The experiment was led by Chris Wang and Jacob Curtis, and we collaborated with really interesting physical chemists at Yale who taught us about these spectroscopy and the Frank-Condon factors and the Doctoroff transformation that goes from one potential energy surface to the other. And we also had collaborations with Liang Zhang at Chicago and Isaac Chuang at MIT, who helped us show that this simulation would have been impossible to perform on a traditional qubit-based quantum computer. And that hardware that contains actual bosons is very efficient at simulating bosons. So I'm happy to stop there and answer your questions.
So if anybody has any questions, please, you can post it in the chat. Or you can unmute yourself.
Now, how about questions? Whoever asks questions, please open your this thing and ask.
Don't be shy. I always tell my students there's no such thing as a dumb question, only dumb answers. So I'm the only one at risk here.
I have a question, sir.
Yeah,
Sure.
please ask.
So, what are the usual temperatures these circuit QED experiments are done? Or
Yeah. So it's about 10 or 15 millikelvin, very close to absolute zero. And the reason, as I said, is that microwave photons at 21 gigahertz have an energy of about 1 Kelvin. The qubit in question has a frequency of about 5 gigahertz, so an energy of 250 millikelvin. So 10 millikelvin is 25 times lower than that, and lets the sort of prevents black body radiation from filling the cavity and exciting the qubit into higher states. It can be cooled to its ground state.
okay. So how can we couple? Suppose there are two cavities, and in like in this circuit QED systems? Suppose if I
So,
want to couple two oscillators, these quantum oscillators.
yeah, okay, that's a good question. So
mm.
I skipped a lot of details in this talk, but that's an excellent question. So in quantum optics or in optics, you have things called beam splitters, which are basically partially silver. They're not, they used to be partially silvered mirrors. They're more complicated these days. But basically, a laser beam going into a beam splitter divides into two parts, one reflected and one transmitted. We have a similar gadget here. We have two cavities, and then we have what looks like a transmon qubit. It's in a slightly different parameter regime, but it's basically one of these antennas. When one arm of the antenna, one side of the antenna is in one cavity and the other side is in the other cavity. And by applying microwave pump tones to that object, we can create, using four-wave mixing, a beam splitter Hamiltonian that moves a photon from one cavity at one frequency and puts it into the other cavity at a different frequency, making them act as if they were just two degenerate oscillators coupled by a spring, let's say. And so that's how we couple together the two modes. And in a controllable way, we can turn that coupling off by turning off certain microwave pumps.
Okay, so the antenna will be connecting both the oscillators, you mean? The antenna connects.
Yes, there's a kind of antenna coupling them, but the two oscillators are at very different frequencies, so they don't couple very strongly. But we supply a nonlinear interaction and a pump, which can change the frequency of the photon in one cavity into the frequency of the other cavity, allowing it to hop into the other cavity.
Okay. So in these systems, what kind of damping can occur, since we are doing this experiment at millikelvin level?
Right.
So
the transmon qubit has some damping due to unknown sources and some dielectric loss in the sapphire substrate, for example, that the antenna is evaporated on. So that limits the lifetime of the excited state of the transmon qubits to 1 to 300 microseconds. Much longer than it was 20 years ago, but still finite. The electromagnetic oscillator is a cavity machined in aluminum, and it can have a Q of 100 million, larger than the lifetimes of order milliseconds, up to maybe even 1 second in certain experiments. In these experiments, they had a lifetime of about half a millisecond. And those are limited by the fact that we open up a little port to drive the oscillator, so that coupling to the outside, and also by tiny sources of dissipation of unknown origin in the surface of the superconductor, which superconductors have zero resistance, zero dissipation at zero frequency, but at microwave frequencies, they have small amounts of dissipation.
Thank you.
Sir, I have a question.
Yes.
That can you you were saying that in the dispersive regime, you were coupling the superconducting qubit with the microwave frequency, and depending upon the frequency of qubit, you are getting a term, transition frequency of qubit, that is shifting the cavity frequency. They are creating a several line width gap. So my question is there any possible way to create macroscopic superposition with that kind of shifted state?
Yes. So we frequently make Schrödinger cat states in which the resonator is in a coherent state, oscillating with a large amplitude and a certain phase, in superposition with a coherent state of the same amplitude but opposite phase. That's called a Schrödinger cat state. And we can use the dispersive Hamiltonian to give us the quantum control that we need to produce such non-classical objects. And for a long time, I think we had sort of world record size of about 100 photons in these cat states. But one of our former postdocs, Serge Rosenblum, who's now at the Weizmann Institute in Israel, recently published a paper with 1,000 photon Schrödinger cat, where the amplitude, that's really getting to be a macroscopic quantum superposition. And he did that using a very, very high Q superconducting resonator with a lifetime of about 35 milliseconds. So really impressive macroscopic quantum superposition.
I have another question that
Sure.
during the boson sampling thing, you were the bending thing can be simulated by squeezing, but I don't understand. I mean, how are you simulating the spatial oscillation?
Simulating the what?
The spatial oscillation, like the vibration one.
Oh, well, so okay, so sorry, just let me get. How do I get back here? So this spatial mode is represented, the quanta in this mode are represented by this cavity, and this spatial mode are represented by quanta in this cavity. The shape, this spatial shape, is not something that we represent. We only need to represent that there's a mode which is different from the other mode, and it has some number of quanta in it. I'm not sure, am I answering your question, or did you mean something else?
No, I am asking, in this picture, you are showing that when it is vibrating, the distance between hydrogen and oxygen is changing.
Yes.
So how are you simulating that in here?
Oh, well, okay. So there's a coordinate of this oscillation mode, okay, representing like the distance, okay? This oscillator has a different coordinate. It's the electric field right here.
Yes.
And we use that to represent the coordinate of this oscillator.
Okay.
And over here, there's an angular coordinate as the bonds bend. And we're using the electric field, the coordinate of this oscillator, to represent that.
Oh.
Does that help?
Okay. Thank you, sir.
But at a more abstract level, those details don't really matter. You just need to be able to represent the excitations of this mode as excitations of some mode in your simulator.
Thank you.
Yep.
Ranjit, you can open and ask.
Yes. Thank you for your talk. I have a few questions.
Sure.
So, can you hear me?
Yes.
Yes. So, in one of your slides, I have seen the Hamiltonian, which contains term relevant for Kerr nonlinearity. Right?
Yes.
Yeah. So, for what purposes? Now my questions. I will start my questions. So, for what purposes do you use it?
Okay. So the if I go back way back here, let's see. Here, and I expand this cosine. There's a phi squared term which looks like an inductor, and then there's a phi to the fourth term which looks like a Kerr nonlinearity. I think that's your question. What do we use that for?
Yep.
Yeah. So Kerr nonlinear terms are used in quantum optics to do many things. To do mixing and conversion of frequency of photons to cause photons to scatter and interact with each other, do parametric down conversion and so forth. We also have ways of getting three-wave mixing, but let's not complicate the discussion with that. So we like to do all the things that quantum opticians like to do with Kerr medium, but typically in quantum optics, this effect is rather weak. You have to have a crystal, and you have to have the photons traveling through this crystal. You have a complicated problem now of momentum conservation, phase matching, it's called. Here, we don't have any of that. We have an extremely strong nonlinear term, and it's in a single mode trapped in a cavity. So we don't have to worry about mode matching and phase matching or momentum conservation. We can see that this Kerr nonlinearity is so strong that the transition frequency of this oscillator, this resonator, from 0 to 1 photon is a certain number, and the transition frequency when you add one more photon differs by 1 or 2 or 3% from this frequency. It's an enormous effect. And so you can use that to treat this as the nonlinearity is so large, you sometimes can treat this as a two-level system if you want, or you can treat it as a quantum mixer that can cause photons entering your cavity to collide and change energy and do all the things that you like to do with Kerr Hamiltonian.
Thank you.
Yeah.
Second question, usually Kerr nonlinearity is one of the mechanisms for the generation of Schrödinger cat states.
Yes.
So do you see cat states in your experiment? And thus, next question related to this, do you use Schrödinger cat states for error correction?
Yes. So as I mentioned, you can use this quantum control that you get from this to create Schrödinger cat states that are very large, even containing up to 1,000 photons. Something that would be very difficult to do in traditional optics. It turns out that if you think of a coherent state with this amplitude as a kind of qubit 0 state, and a coherent state of this amplitude as logical 1, you can encode a qubit in such Schrödinger cat states. A linear combination of 0 and 1 being a superposition of two coherent states, and therefore a cat state. It is possible to use such an encoding to create error correcting codes. And in fact, the first experiment to achieve break even, where the logical qubit lifetime was slightly longer than the best physical qubit, was done by my colleague Rob Sholkoff using a Schrodinger cat code where logical 0 was a cat like this, and logical 1 was a cat where the two states are separated in momentum instead of position in phase space. And they both have even parity, even photon number. And by measuring the photon number parity, again, something we can do with this strong Kerr effect, we're able to see whether a photon has been lost and correct for that.
Okay, thank you. So the last question, what is the frequency range of this Kerr nonlinearity? Is it in optical range or microwave? Or
no, this is all microwave, yeah.
Microwaves, okay.
Yep.
Thank you.
Sure, my pleasure.
Are there any more questions?
So
Looks like-
in this slide, the C equal to Cj plus C geometric you are writing. So what is that? The
I'm sorry, I
capacitance,
can't hear you very
capacitance?
well. Can you repeat?
The CE in this slide, you wrote CE equal to Cj plus C geometric, the capacitance, effective capacitance.
Oh,
Probably.
yeah.
Oh, where does this come from?
Oh, okay. Sure. So the question is, this is the total capacitance, some junction capacitance, and some geometric capacitance. So if you look at this Josephson junction, it's got, where's my picture of it? Well, I've lost it, but there's a little Josephson junction, which is two small pieces of metal very close together, separated by a few nanometers, 1 or 2 nanometers of oxide. That is a capacitor. It's not very big, but the plates are extremely close together. So it has some significant capacitance. So I call that the junction capacitance. And then there's this big antenna pads. And if the collective excitations of the qubit are Cooper pairs sloshing back and forth, causing the antenna to oscillate. And when you have more Cooper pairs here and fewer here, there's an electric field that goes from one antenna pad to the other, and this has stores some energy, and this is what I call the geometric capacitance between these two large 0.5 millimeter pieces of aluminum. Does that help?
Yeah, thanks.
Yeah. So this is actually I forget. I think this is about 10%. That tiny thing has nearly 10% of the capacitance of this huge thing. So they're both important.
Okay.
Okay, so looks like no more questions. So time has come to thank Professor Girvin for a wonderful talk, very enjoyable evening here. Thanks a lot. And we hope to see you here sometime in person.
Yes, thank you so much. And I appreciate all the questions from the audience. Thank you very much. Bye-bye.
Thank you. Bye.